All right. Last time we left off, we started talking about query execution. So this is the step where you've built your index, you have a query, and now the goal is to get the set of results, get the set of scores as quickly as you can. So we started talking about the docatatime strategy, and we're going to keep talking about it today, and also talk about term at a time, and then some ways to optimize the execution. So document at a time, we talked about the way you're doing it. Basically, you have k lists, and you're doing a linear merge. And as you're merging, you're computing the scoring function for each of the documents. Now, so what is the simplest way to implement docatatime? The simplest way to do it is by doing pairwise merges of each term in the query, of the inverted list for each term in the query. So now let's see how this works. So we know that linear merge is actually optimal when you have two lists, right? So if you have two lists, their lengths are NA and NB, the cost of the merge is N of A plus N of B plus whatever times whatever constant you have, and this is as good as you can get. This is as good as it can get for merging two lists. But what happens if you have a multi-word query? Right? So if the query is just A and B, then it's obvious how to do that in the best possible way. So what if you have many lists that you need to merge? The simplest way you could do this is you could merge the lists one by one, right? So you have a multi-word query, you take the inverted lists for A and B, you do the linear merge on them, you take the result, let's call it R, merge the result with inverted list for C, merge the result with inverted list for D, and so on and so forth until you finish all the query words, right? So that is the simplest way to do it. It basically just requires you to implement vanilla linear merge, and then you're all set for that. By the way, this is the one. This is the one where this is the one which you're expected to do in the coursework for task 3, I guess, the basic document at a time thing. So, but let's see how this works complexity-wise, how costly this is. So, you would expect the cost of this to be linear in the number of entries in the lists, right? So if list A has N of A and list B has N of B entries, then you would sort of expect that to be the overall cost of merging them one by one. And it turns out that that's not quite the case. The worst case is actually not the order of n, but the order of n squared. That seems a bit counterintuitive, but let's see how that comes up. So suppose I have 5 query terms, and these are their inverted lists, and let's say I do the naive variant of merging. So what happens? I take the first 2 query words, I do the linear merge, and that merge is going to take on the order of 4 plus 2 operations, right? Because what I have to do is I have to put I put the pointer here, put the pointer there, and just advance them one by one. At each iteration, I'm advancing only one of the 2 pointers. So I have to do 4 plus 2 operations, right? So now my resulting list R has 6 entries, and what I'm going to do is I'm going to take this list and merge it with the next, with the inverted list for C. So that's going to take 6 plus 1 operations, because I have 6 and 1 here, right? Right. And then at the next iteration, my inverted list is going to be longer. And as I keep doing that, what you will notice is one of my lists is getting longer and longer and longer, and the other list stays fairly short. And I still have to iterate over that entire list every time I do the linear merge, right? So that's what's happening every time in the naive version. Now, how did I get to n squared? What is the worst case scenario for this? The worst case scenario is I have a query with a bunch of rare words, right? So cryogenic aardvarks and a bunch of other words like that. All the words that occur one time in your collection, and I have n of those words, right? So in that case, my complexity is going to be, so I'm going to have 1 plus 1 for the first 2, and then 2 plus 1, and then 3 plus 1, all the way up to n minus 1 plus 1, right? And that's just a nesting sum, and you know that that's n squared plus n over 2. So that is where the n squared complexity, worst case, comes from. So If you have a query with lots of rare terms, then this naive merging strategy ends up being a lot more expensive than it should be. If you have a query with long lists and not too many of them, then this is actually a very reasonable way of doing it. But if you have lots of short lists, this is really bad. So can we do any better than this? Well, let's try. So what if we were not lazy? The one on the previous slide is basically lazy, right? Because linear merge isn't that hard to implement, and that is just basically putting a loop around the linear merge. So what if we weren't lazy and we tried to actually write a k-way merge, which is not that trivial, by the way. What's the simplest way to write the k-way merge? The simplest way is, again, we have our 5 inverted lists, but what we're going to do now is, instead of merging them in pairs, we're going to put a pointer on each one of the lists, and then sort of process all the pointers at once, right? Loop over all the pointers, increment the smallest one, compute the score for the one that we've incremented, and keep doing that until we've processed all the documents. So the algorithm will look kind of like that. So you have k pointers to the beginning of each list. You find the smallest pointer, the pointer with the smallest document ID under it. So it would be this pointer right there. You look at whether any other documents, whether any other pointers point to the same ID. If they do, you take them all together because they all refer to the same document. You use them all to compute the score for this document with the ID, and then you increment all of them, right? And then you repeat that until you have no more IDs, right? So that seems like that should do better. So let's look at the complexity of this. So this step, finding the pointer with the smallest ID, how many operations that's going to take. In the simplest case, what you're doing is you have k pointers and you just iterate over them, right? So you have a little loop that goes over the k pointers. So that's going to take k operations. So this step takes k operations. And then computing the score, so that's going to depend on the number of matches, right? So that's a bit unknown, but it actually it becomes a bit easier if we look at the following steps, right? So how many times will we have to do this procedure? Well, we will have to do this until we have no more documents in the list, until all the pointers increment beyond the end of the lists, right? And this can happen in a number of ways. So here we're incrementing a bunch of pointers, right? So let's say that we increment only one pointer at each stage, right? So no two lists contain the same document, so this way we would increment only one pointer. This means that we would repeat this loop n times, where n is the total number of entries in all of the lists. And that also means that in the body, when we're computing the score, we're only the computation of the score will involve only a single post. So that's a single cost operation, right? You could sort of pretend that it's a constant, right? So what happens on the other hand? What if we increment, what if the lists are dense and they all point to the same documents? In that case, what would happen is you would increment, in each iteration, you would increment k pointers, and the score computation would involve k operations, but then you would run through the IDs k times faster, right? So it actually doesn't matter which way you slice it. A combination of this and repeating it is going to take n operations, where n is the total number of entries in the list. So what we have is, in the worst case, but that guy is actually the same. Finding the minimum of the k lists, you always have to do that, right? So in the worst case, you're going to have n iterations, and within those n iterations, you have to find the minimum each time. So that takes k operations. So your cost is going to be k times n in the worst case. And again, our worst case is where you have n tiny lists, each of which has only one document in it. So in that case, k equals n. And your worst case complexity is, again, n squared. Okay, right? So we tried, but this doesn't actually do any better than the one that we had on the previous slide. This is not any better in the worst case. Can you do better? Yes, you can. If you look at this algorithm and you try to figure out, well, what is the sticking point? Where is it wasting? Where can we make it a little bit better? Where is it wasting time? And the place where it's wasting time is right there. It's when you're finding the smallest one. Why are you wasting time? Well, think about what you're doing. Right? You've got 5 pointers. You want to find the minimum. So you have a little loop that runs over them, right? And you have a running min, and you say, let's say you start here, right? Is 53 the minimum? No. Is 51, 37, 2? Yes, 2 is the minimum, right? Now then you increment 2 to 5, and now you have a new list of 5 pointers. But 4 out of those 5 are the same. They haven't changed, right? So 20, 37, 51, and 53, they haven't changed. So at the next iteration, when you're running the loop over the new 5 pointers, you've actually seen 4 of them. So you shouldn't be doing that again. That's a waste. There's only one new element. You should really just maybe sort of compute the second best and then compare the second best to this new thing that enters, right? That would work, except if you popped 2 things in the previous count, then the second best wouldn't do anything for you, right? So what do you do? It turns out that in the general case, the way you can get around this is by using a priority queue. So what a priority queue would allow you to do is it will allow you to keep keep the pointers in a data structure where you could find the minimum overall in a logarithmic time rather than linear time in the size of the elements. So this is what it would look like roughly. So you would have a min-heap. You would store the k pointers in the min-heap, and then the way it works is you pick the smallest ID. So you see what is the minimum element on my heap. You pop all the elements, all the pointers that point to that ID, and there could be one of them or there could be a number of them, right? Then you compute the score for that ID again. It could be in a number of lists, so you have to pop all of them, and the score has to compute over all of those, because basically multiple pop elements mean multiple query words occurring in the document. And then once you've computed the scores, what you do is those pointers that you have popped, you increment them, so they will point to the next elements in their respective lists, and you push the incremented versions onto the heap. Right? And then you repeat that procedure until you have no more IDs. So that step, in the worst case, is still going to take n operations. Peaking is constant. Popping, in the worst case, you're popping 1, so it is constant. But this part is logarithmic, right? So when you're pushing elements onto a heap, it takes log k operations to push a new element to a heap. And you're gonna, in the worst case, you're gonna do that n times. So this becomes our new expensive point, right? So in the worst case, you're gonna have, so overall the cost is n log k, and in the worst case, it's gonna turn into n log n. Again, the worst case is you have a query with n singletons, so n words that occur one time in the collection, and they're always in different documents, so there's never overlap of any kind. That's your worst case.